All right, so I'm going to try to record your magnetism review problems. Had about 8 minutes recorded and then it had some issues, so we're going to hopefully not have issues again. All right, number 1 says near San Francisco, where the vertically downward component of the Earth's magnetic field is 4.8 times 10 to the minus 5 Tesla. So I'm going to say that that's B, 4.8 times 10 to the minus 5 Tesla. And I have a velocity for my car of 25 meters per second. And as a result, I have an EMF developing as my car moves through the magnetic field. And that EMF is 2.4 times 10 to the minus 3 volts. And it wants to know in part A which side of the car is positive, the driver's side or the passenger. So here's my car. This is like the width of the car, which I got to find in part B. So I'm going to call that my L. And it wants to know which side is positive or negative. So I'm going to have to do the right-hand rule. So what I'm going to do is I'm going to use my right hand. And I'm going to talk about the force acting on a positive charge. So I'm going to point my 4 fingers down into the earth. I'm going to point my thumb forward, and my charge is going to be pushed to the left. So my positive charge is going to be pushed to the left, so that's the driver's side, so it's going to be the positive side. All right, so I had to stop for a minute because someone came in the room, but I think what I was saying to you was that if we did the right-hand rule, point our 4 fingers into the earth, our thumb straight forward, then the force applied to the positive charges is going to push them over in this direction, so this is going to be the positive charge side, which is the driver's side. Okay, now we got to do part B. Part B wants to know what is the width of the car. Well, you have an equation that says that EMF is equal to BLV, and your EMF was given to you as 2.4 times 10 to the minus 3 volts. I want to divide that by my B, which is 4.8 times 10 to the minus 5 Tesla. And then I want to make sure that I include the 25 meters per second. So there's my L, my width of my car. My L is going to be 2.0. So I'm done with number 1. Yay! Maybe no one else will interrupt me, and we're going to go on to number 2. Okay, number 2 says to take this light bulb out and just put a wire there. So I have complete connection. I have minimum resistance from the wire and the rods, the wire and the rails that this rod is going to ride on. This rod is going to have some resistance, and that's going to be rho L over A. And they want to know what the current is in the rod. So we know that I is equal to V over R. I've got the R for the resistance of the rod that I'm going to calculate here in a minute. I need this to be the EMF. Well, the EMF is BLV. So B is going to be 0.050 Tesla, 0.050 Tesla. I have no idea what L is, so I'm just going to put a variable there. And it's moving at a speed of 2 meters per second. So if I did that math correctly, my EMF is going to be 2 times 0.05 or 0.10 volts. So there's my EMF. Now I got to get my resistance. Well, my resistance is rho, and rho is 9.7 times 10 to the minus 8. Okay, let's fix that. 9.7 times 10 to the minus 8 ohms times meters. No value for L, so I'm just going to call it L. My area was given to me as 3.1 times 10 to the minus 6 meters squared. So when I solve for R, I'm going to get 0.0313. Check my units out, ohms over meters. And then I still have that L in there for the length because I don't know what that is. Well, if I go back over here and substitute in now, this is 0.100, and it'll be Tesla meters per second times my L, which I don't know what it is. I'm going to divide that by 0.0313 ohms over meters times L. These will cancel, and I will wind up with 3.2, and my units will be amps. Now, if you're curious as to why that's amps, you can work through the variables and the units and figure it out. If you don't want to do that, come by and I'll show you. It's a little convoluted, but it's doable. All right, let's see if I can clear this off and go to number 3. Okay, we're going to pull it on down, talk about number 3. There we go. All right. So on number 3 it says, the electrons in the beam of a television set have a kinetic energy, so Ke is 2.4 times 10 to the minus 16th joules, and they're electrons. Initially, the electrons move horizontally from west to east, so they're moving like that with a velocity v. And the vertical component of the Earth's magnetic field points downward towards the surface of the Earth and has a magnitude of 2 times 10 to the minus 6 Tesla. And part A says, in what direction are the electrons deflected by this field component? So I'm going to use the left hand because it's electrons, and I'm going to say that my fingers need to go down into the Earth. I'm moving from west to east, so my force is going to be to the south. So my electrons are going to be pushed to the south because that's the direction of the force. Okay? Then B says, what is the acceleration of the electrons in part A? Well, I want the acceleration. So what I did was I said, okay, well, I know that F is equal to BQV. And then I also know that net F equals MA. So the net F is caused by the magnetic field of the Earth. So I'm going to set BQV equal to MA, or BQV over M will give me A. Now it becomes a plug and chug. B was 2 times 10 to the minus 6 Tesla. Q is the charge on an electron, 1.6 times 10 to the negative 19th coulombs. And my velocity was given to me as, let me go back and read that. Oop, don't know that, do I? But I can use the kinetic energy, 1/2 mv squared is equal to Ke. So 1/2, my mass of an electron is 9.11 times 10 to the minus 31st kilograms, and I would give that value to you. Don't memorize it. My V is what I'm looking for, and my Ke, they told us, was 2.4 times 10 to the minus 16 joules. So I can solve for my velocity, and when I did that in a much neater fashion than I'm doing right now, I got 725 87432, 87432. So that's going to be 72,587,432 meters per second. So I'm going to plug that in for my velocity, 72,587,432. So there's my BQV, and I'm going to divide that by the mass of my lovely little electron, 9.11 times 10 to the minus 31st kilograms. And when I did that and did it correctly, I found the acceleration to be 2.55 times 10 to the 14th meters per second squared. So there was number 3. None of these are very hard yet. Let's go on to number 4. So let me clean this up and get us to number 4. All right, so we're going to drag it on down here to number 4. Okay. It says, suppose the light bulb in figure 22.4b, which is this one here, is replaced by a 6-ohm electric heater. And the power is 15 watts. And we're going to move our rod to the right with a constant speed. And we know that this magnetic field is 2.4 Tesla, and the rod is 1.2 meters. How fast is the bar moving? So first of all, I said, well, I need to find out the EMF. The EMF is equal to BLV. And I don't know anything about my EMF, but a long time ago I taught you that power was equal to V times I. And then I said, well, if you don't like that, I can say that power is equal to V squared over R. So power times R, square rooted, would give me the EMF, or the voltage. So the square root of PR is equal to BLV, or L is equal to the square root of PR over BV. So now I'm going to plug in. So that's going to be 15 watts. and they told me that it was a 6 ohm resistor. So I have what, 90 up there, the square root of 90, divided by B, which was 2.4 Tesla. And I'm looking for the velocity, so it might be better if I actually look for what they asked me to look for. So that should be the velocity. Doesn't look very good. So this should be the velocity, and then I should have had the length right here. So the length is what they gave me of 1.2 meters. 1.2 meters. So I'm going to solve for my velocity by taking the square root of 90 and dividing it by whatever 2.4 times 1.2 is. And when I did that, I got velocity to be 3.3 meters per second. Okay, so there's number 4. Number 5 says the drawing shows a straight wire, a part of which is bent into the shape of a circle. The radius of the circle is 2 centimeters. A constant magnetic field of 0.55 Tesla is directed perpendicular to the plane of the paper. Someone grabs the end of the wire and pulls it taut so that the radius of the circle shrinks to 0 in a time of a quarter second. Find the magnitude of the average induced EMF between the ends of the wire. Okay, so I'm looking at a change in flux over a change in time. So a change in flux is going to be B delta A over delta T, because they're really just changing the area as they pull the wire taut. Okay, so I said, well, B is given to me as 0.55 Tesla. The area is going to go from pi r squared to 0, so the change in area is going to be pi r squared, 0.02 meters squared, minus 0, because I took it to no area left at all, and then that happened in 0.25 seconds. So I should be able to find the EMF induced. And so I had to multiply pi times 0.02 squared, and then multiply that by 0.55, and divide by 0.25, or multiply by 4. It doesn't really matter. And when I did that, I got the EMF to be 2.76 times 10 to the negative 3 volts. So there's number 5. All right, let's scoot on down to number 6. All right, number 6 says, a rectangular loop of wire is moving toward the bottom of the page with a speed of 0.02 meters per second. So there's my V, 0.020 meters per second. The loop is leaving a region in which a 2.4 Tesla magnetic field exists. So there's B, 2.4 Tesla. And the magnetic field outside this region is 0 during a time of t equals 2 seconds. What is the magnitude in the change of the change in the magnetic flux? So I am being asked to find my delta phi. So delta phi over delta t. So EMF times delta t is equal to the change in flux. All right. So let's see what we can do with this. Well, we know that the EMF is VLV. The B is 2.4 Tesla. The L is 0.08 meters. And that's always going to be the dimension that they're pulling on. That's the dimension you're going to use for the length, that right there. And they're pulling it at a rate of 0.020 meters per second, which is not a very fast pull. So when I did that, I got the EMF to be 3.84 times 10 to the minus 3 Tesla. I'm sorry, that's volts. So now I can go back over here and finish it up. 3.84 times 10 to the minus 3 volts. And I'm going to pull it for a period of 2 seconds to get my change in my flux. So when I did that, I got 7.68 times 10 to the minus 3. And that's going to be measured in Webers. And that's my change in flux.